It's you.
Okay. Good?
Yeah.
Wonderful. All right, so does anybody who has looked at the assignment on this all this gravity stuff have any specific questions?
All two of you.
All two of you.
I do, but I don't want to feel stupid.
Oh, come on. Look around you.
It's a dark
Let me
field
process
here.
for a second.
Number 4. Yeah, look at me and then you should feel bad.
Number 4.
Okay, yeah, it was
Number
4 that I just
four.
questioned. 4.
Okay.
Get numbers 1.
Yeah.
Is this the shrunk the earth?
Yeah.
Okay. There's a couple of ways you can do this problem. But let's look at, first off, you got to start with this equation here. Big G mass of the earth over r squared.
Which one is this?
Number 4. So on number 4, you're talking about the gravitational acceleration on the surface of the earth, right? So here's the deal. If you plug in big G, the mass of the earth, and the standard radius of the earth, 6.3713 times 10 to the 6 meters, and you plug all of those things in, what are you going to get? 9.8 meters per second squared. That's what you're going to get. 9.8 meters per second squared. Boom. There you go. So what we're saying is that we're going to take the radius of the earth and we're going to keep the same mass, so we don't have to worry about changing the top. So what's going to happen on the bottom? By half. So if you want to do smash mouth physics, take big G, mass of the earth, take the actual radius of the earth, 6.3713 times 10 to the 6 meters, take that radius of the earth, divide it by 2, square it, get a number. Okay? Now, think this through. So here's the earth, and we're going to shrink it down. So what do you think is going to happen to that value of G? It's going to get bigger, or it's going to get smaller? Bigger, because now the mass of the earth is going to be the same mass, but now it's going to be a lot more compressed. And now, if you look at the earth and treating it as a point mass, now when you're standing here, okay, we're now much closer to that same mass, okay, because we've reduced the distance. So our gravitational acceleration is going to be much greater because we're going to weigh more. Okay, it's going to be it's going to be much harder to jump. Okay, much harder to jump because your gravitational acceleration is going to be so much higher. So this is the smash mouth physics approach. Take the radius of the earth, divide it by half, do all of this, it works, you're going to get a number. Then divide that by 9.8 meters per second squared because you want a comparison. Okay? That's one thing that you can do. If you like smash mouth physics, go with smash mouth physics. It works, go with it, it's grand. Okay? It's one option.
Ooh, your phone screen's cracked. We're good.
Thanks. Okay, now here's option number 2, which is a little bit more elegant and actually easier. So the more elegant approach is to say, okay, this is my initial value of gravitational acceleration. I don't know what it is, I don't care what it is, it's just G. Don't know, don't care. But now, my new, call that G prime, my new gravitational acceleration. I'm not going to change anything on the top, okay?
Thank you. Please.
But now, what am I going to do to the radius? Mathematically, what do I have to do to reduce the radius by half? Bless you.
You multiply it by half.
Or divide by 2.
Yes, whatever.
Okay? Same thing.
Okay.
So
You looked
I'm
at me
gonna
really
take the radius
disappointed.
and divide it by 2, but then that's going to get squared, right? That's going to get squared because it's over r squared. So this becomes big G, mass of the earth, r squared over what? 4, right? So the 4 is in the denominator of the denominator. So what's going to happen to the floor? To the 4. It's going to go up. So you get 4 times big G, mass of the earth, over r squared. Well, this was my original value of G. So G prime is going to be 4 times greater than the original value of G. So if you look at it this way, it saves you the hassle and the potential screw up of plugging in all of these numbers. You just look at it, oh, yeah, right. Now, interesting thing would happen. What if I reduced the mass of the Earth by half, like this, but then at the same time I double the mass of the Earth. So I reduce it by half, but then I double the mass of the Earth.
So you double the half?
No. I'm still going to shrink the Earth down to half of what it was.
Alright.
But at the same time, I'm going to make the mass twice as big.
Multiply it by 8.
Yes, because then this would be 2 times this. So then G would go up by a factor of 8. Now, what if I kept the radius the same, but just doubled the mass of the Earth? Then what would happen to G? Then it would just double. Okay? So it's, when you start playing with this, it becomes much easier if you just look at it as a ratio as opposed to actually plugging in the numbers. You can do it that way. It's just not very efficient. Okay? Does that make sense? Okay, now let's talk about number 6. Okay? Let's talk about number 6 with the electron and the proton. Let's talk about it. Let's talk about it. So your answer to number 6, so here's this proton.
Yeah.
Okay?
What number is this?
Number 6. Okay? So here's this proton. Okay? And then here's this electron. Right? And this electron is moving around out here. So, from a historical perspective, this was like after Rutherford had done his work and said, okay, hey, we have this dense nucleus. Okay, did the gold foil thing. And they said, okay, well, we're just going to let the atom look like a miniature solar system. They'd all been trained in Newtonian mechanics. This is in our wheelhouse. Hey, we know how to do these calculations. Problem solved. This is easy. So they said, all right, here's the mass of a proton, here's the mass of an electron. But problem is, the gravitational force wasn't enough to hold this electron in orbit around it. Okay? Gravity's strong enough to hold the Earth in orbit around the sun. That's cool. But there wasn't enough gravity to hold the electron, because literally, it would be like me trying to swing Hank the bowling ball around over my head with like this very, very thin piece of string. It wouldn't work. Okay? Gravity isn't enough. So, the first thing I want you to do is just straight F equals big G, mass of the electron, mass of the proton, over R squared. And that should be a very, 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 very small number. Okay? Like 10 to the negative 40 something. Okay? It's going to be really, 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 really small number. Then you want to compare that to the electrostatic force caused by oppositely charged particles. Okay, you have negatively charged electron, positively charged proton. So if you look at that one, okay, that is on a comparison, and some kids, well, I don't know what to do. Well, let's look at it this way. Let's say Hunter has a job, and Hunter makes $24 an hour. I have a job, I make $8 an hour. How much, what's the ratio of Hunter's wage to my wage? He makes 24, I get 8.
3 to 1.
3 to 1. How'd you get that?
Divided 24 by 8.
Yeah, so you took the bigger number and divided it by the smaller number. So that's what you're going to do there. To get this, how many times greater the electrostatic force is than the gravitational force, you're going to take that electrostatic force and you're going to divide it by the gravitational force. That, in contrast, should be a really, 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 really big number. Okay? Like something around, and this is an ish, something around 10 to the 40th. Okay? So your answer to 6B, ish, should be around 10 to the 40th. Ish. Okay? Now, what I want you to do on C is this. So here's what's going to happen on C. I would say, okay, how big would that proton have to be to have an electron that's that small distance away, with this electron being 10 to the negative 31st kilograms? So in other words, If I want this attractive force to be 8.2 times 10 to the negative 10th? Negative 8. Yeah. Okay? So that's going to be my FG. Okay? That's what this is. That's going to be my FG. So that's going to equal big G, mass of the electron, which you know, times the mass of the proton, which you don't know, and then divided by distance squared. So this becomes your FG. You know what big G is, you know what the mass of the electron is, you know the distance, the only thing you don't know is the mass of the proton. The mass of the proton is going to be really, 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 really big.
We get it.
Ah,
That's
perfect.
even better.
Okay.
M, E,
Mass of the electron, mass of the proton, d squared. You know everything but the new mass of the proton. It's going to be a really, really, really big number.
Like bigger than 10 to the 40th? or-
Oh, no, not that big. But just on a relative scale of
But really, really big.
that it's going to be
Not
big.
really big, just really, really.
It's not like super.
Maybe 10 to something around your first teenage birthday.
How many protons do you think are in my body?
At least 7.
Functional or present?
What do you mean, there are functional?
All.
It's meaning
So you can
Hunter's missing a couple protons.
Well, to give you some comparison, okay? A spoonful of sugar roughly contains Avogadro's number of carbon atoms. Okay?
6.2 times 10 to the 20 something. So third.
23rd. Okay, that's a spoonful of carbon atoms.
Alright.
Okay, that's a spoonful of sugar, that's 6.02 times 10 to the 23rd. Now, that's just the number of carbon atoms. Multiply that by 6 to get the number of carbon, the total number of protons just in all the carbon atoms.
It's a big number.
Big number.
That's like,
Now, that's just one spoonful. So,
So the real question is-
you're a lot of spoonfuls.
How many
if anyone
spoonfuls?
needs a couple protons,
You have some to spare.
I got some spare.
Okay.
We got a lot of G's.
Maybe you
He's
put-
got a lot of G's too.
I got a lot of protons. And electrons. Probably
Okay. Oh,
No croutons.
no. Protons, electrons, neutrons, persons. Okay. Now, let me take you through a couple of things on 13 and 14. So on 13, you want to find the radius of the satellite in a geosynchronous orbit, meaning that the period is 24 hours. But the ultimate question is how far above the surface of the Earth. So you're going to get a value of r, which is going, and that's from the center to center distance. And that radius, your initial radius in number 13, after you solve it, should begin with the number 4. Okay, so it should be 4 point something. So if you do 13 right, this is before you subtract out the radius of the Earth. Okay, so when your initial radius from the center of the Earth out to this satellite, that radius should start with the number 4. Okay? Your final answer on 13, though, is going to end up something to the 7th. Okay? So your initial radius is going to start with the number 4. After you subtract out the radius of the Earth, your exponent should be something times 10 to the 7th. On 14, it's the same type thing. You're finding how far above the space shuttle is above the Earth. When you get done with 14, that answer should be something times 10 to the 5th. After you subtract out the radius of the Earth. Now, when you do 15, because you want to find the orbital velocity of the space shuttle, listen to me. When you do 15, you're going to use the radius that you found in 14, but you have to use the radius before you subtract out the radius of the Earth. So in other words, when you do 15, don't use the final answer from 14. Use your answer that you got before you subtract out the radius of the Earth. Okay?
You said 13 was 10 to the 6th.
No, 10 to the 7th. 10 to the 7th. Your answer to number 11 in minutes, this is a big-ish, should be around 100. That's a big-ish. Okay? That's in minutes.
Minutes.
Okay? That's in minutes.
So we have to.
Which one?
Number 11 in minutes
Minutes.
should be around 100, and that's a big-ish.
100 minutes.
Okay? It's an ish, not exactly 100.
So.
180.
180. Like, is that how big of an ish it is?
No, not that big of an ish. No, that's big-ish.
Like 100.
It's not that big of an
90
ish.
to 100.
90 to 110. Yeah,
80 to 100.
So you could have
90
just said
to
around
100.
100.
I know.
90 to 110.
Okay, so we're good with that. So, here's the drill. So for the test on Monday, okay, there's two distinct parts to the test on Monday. No. I'm not that big a jerk where I
Big
was.
dog and no big dog.
Yeah. Son big dog with the big dog. So here's your two distinct parts.
Just his face when he walked
One
in the
comes, the
door.
other one leaves, you know.
Yeah, that did time that well. Though.
Equal and opposite.
Okay.
Okay.
If you get that custom made, back.
Okay. Anyway, shh. Back to our story.
You gonna be at the game tonight, Mr. Rickman?
Maybe.
Right.
You should be the announcer.
Yeah. Throw in some of your comedic.
I feel like they would all be very dark.
Oh, there was some serious conservation of momentum going on up there.
You need to use
Couldn't you
more
just do
force
like a
supply to
play-by-play
make
one
that
game?
Oh, pass was long. Too much VX, not enough VY. He dropped the ball, coefficient of friction too low, penalty, throw the flag.
I like it, personally.
Anyway, so I don't think they want me to.
I would enjoy that. I would really enjoy that.
I know. Okay.
You have a good weekend,
I will, study hard. Okay, so now that we have my football announcing career sorted out, all right. So there's two distinct parts to the test. There's the centripetal motion part, and then there's the gravity part.
Those are
Okay. So
notes, dude.
no, I'm talking. I was on such a roll. You show up and everything just goes south.
Why is that?
We were really
Because
on
it's
track.
Be really distracting.
Yes, you are. You're very distracted, so stop. So, with the centripetal motion part, there's two distinct parts within that. So, you're going to have, within the centripetal motion, so here's the test. We'll do a little flow chart.
What was that?
Okay?
What is that?
Wow.
A test. It says test.
The electrons.
Okay.
So, you're
That was
going to
a pretty little
have
break.
centripetal motion, and then you're going to have gravity. Okay? So within the centripetal motion, you're going to have vertical, and then you're going to have horizontal. Okay?
Barely remember that.
I don't remember.
This is why we're reviewing. So the vertical is when you're swinging it around in a circle like this. There's two things you have to worry about. What happens at the top and what happens at the bottom. How do you find the total force at the top?
FC plus FG.
No, at the top.
FC minus FG.
Yes. So
I
at
don't
the
remember
top
this.
is force centripetal minus Fg equals force total.
So at the top.
Now, this force total is what you experience, okay? And I will tell you, hey, you want to feel a half a G. You want to feel 3/4 of your weight, something like that. So at the top, you always start with this. You always start with this. So if I say, hey, I want you to feel weightlessness, you make this 0 Fg. If you want to feel half your force weight, make this 1/2 Fg. So let's say that you want to feel half your force weight. You want to feel an acceleration of 4.9 meters per second squared. So here's the deal. You go 1/2 Fg equals force centripetal minus Fg. There's one like this on the review. What can you do with your Fg's?
Adam.
Add them together so you get 3/2 mg equals mv squared over r. Masses cancel out. You can go from there. So this is what you will experience. And this will be a fraction of what you feel right now. I could double it, say, hey, how fast do you have to be going at the top of the loop to feel twice your force weight? It's the same process. The only thing that ever changes is what goes in front of that Fg. Okay? That's the only thing that ever changes.
Did you cross out the radius by accident
what
or
you-
like?
What happened there?
No, I meant to cross out.
Okay,
Alright,
okay,
so
good.
yeah,
I was
3/2.
really confused.
So you have 3/2.
Ng
Why'd you cross out the
equals
mass?
VR.
Because you have the same
No,
mass on
and
both
cancel
sides.
So you have 3/2.
So you've got 3/2 g
Okay.
equals v squared over r.
So
So
Okay.
typically you're going to know the radius, you want to find the velocity. So in this case, the velocity would be 3/2 go.
what happens?
Is that GER on the equation sheet?
No.
No?
The only thing that's on your equation sheet is mv squared over r and fg equals mg.
Are there other like hidden ones that we need to, know?
Why is this
one big No. curve
not in the equation sheet?
Because it's such a limited use equation.
Are we given it?
If it gets used, I feel like it should be on the big dog.
It's like V
Like
equals.
what would be used?
Like the test question we're gonna have.
I feel like we're gonna use it on the test, otherwise you wouldn't go over it in the review.
But
Yeah.
here's my point. If I said you want to feel 1/4 Fg, then this would be 1/4, and then this would become 5/4, and this would become 5/4 girth. So I'm not going to put every possible combination of a fractional thing on your equation sheet.
Can't you like say?
V squared over R. Got
Yeah,
it.
no, I was just talking about why is the square root of GER not on the equation sheet? Not necessarily with the value in front of it, but just the equation.
Because the only thing that changes is that you make this 0 Fg.
I actually understand what he's saying. Because this,
Hold up.
it says V equals, that's just another way to calculate the velocity.
No, you technically get it because you multiply the r over and then you square root, so you don't need the GER. Do you see?
You can if you're in the state of weightlessness. If I say, what's the minimum velocity that you have to complete a loop, this becomes 0, and then you have mg equaling mv squared over r, okay? So if you're at the top and you're weightless, the masses cancel out, and then it is just v equals the square root of GER.
So Fg equals Fc minus Fg.
At the top.
At the top.
At the bottom, what do?
Add it.
You add it. So you have two extremes, and it's going to be one of the extremes. It's going to be at the top or at the bottom. Okay?
So you crossed out M when you have FG on the other side.
Because
Because
g equals
As
mg.
G
Fg
equals
is mass times gravitational acceleration.
Dude,
So
I'll
you
lend
just
you a couple
substitute.
protons.
So look, at the top, okay, what you feel, that total force, is always going to be force centripetal minus Fg. Okay? This is going to be what you feel, which is going to be a multiple of your weight.
Yeah.
Let's say you want to feel twice what you weigh right now. So you're going to have 2Fg equals force centripetal minus Fg. You're going to move this over here. 3Fg equals Fc. So that's 3 times mg equals mv squared over r. Masses cancel out. Solve for velocity.
Alright, so let's talk about a trick question you're gonna ask on the multiple choice.
The trick question.
That's the point.
I'll think of something right now and ask some
So
crazy
what-
scenario you'll have there.
Okay? All right. Let's throw this down. Here's a bucket with some water as it's being swung around. Okay? So I got a bucket and I'm swinging it all the way around. Okay? What are the forces acting on the water at the top of the loop?
The
Centripetal force.
Acting which way?
Inward.
Okay?
Inward and at a right angle, right?
To
the velocity vector.
velocity vector. Okay, got that.
Gravity.
G.
Gravity.
That's
Anything else?
it.
That's it.
Yeah.
Why was that tricky? Was that
Is that a trick question?
was it a trick
That's
question?
gonna be on his multiple choice.
I don't know.
It's.
Alright, how about?
Don't make it complicated.
It's
What's the
too late.
friction?
Is there any force from the inside pushing it out?
Alright, but on the velocity time.
No, 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 no. Here's the question. Is there anything on the inside of this thing pushing it out?
No.
No.
No. Okay? What does the water want to do at this point? The water wants to go in a straight line. Now, think about this. If I swing a bucket around in zero gravity, okay? I swing the bucket around in zero gravity. Is there any minimum velocity that I have to have at the top?
No.
Why?
It's already at 0 G.
Yeah, there's no gravity pulling it down that's going to make it fall. So if I swing this rubber stopper around in a gravitational field, right? And if I'm not going fast enough, it doesn't complete the loop. But in a gravitational field, I have to be going fast enough to complete that loop. Now, if I swing it around in a horizontal loop, is there a minimum velocity that I have to have? No, because even if I slow down, right, got this action going, there's no real minimum velocity. So there's a minimum velocity in the vertical, but there's not a minimum velocity in the horizontal. Okay? Good with that. Now, Bubba in a barrel.
I hate it.
I hate Bubba.
Why?
I appreciate him. I value him.
Literally. And I will say, Bubba is in a barrel. Literally.
Bubba needs to
That's
get
how the test is going to be.
out.
Bubba is in the barrel,
Get out of the barrel.
and we've dropped out the floor.
Line up
Get out.
the-
Brooklyn. Bubba is on the Bubba is in the barrel. You've written this right.
What you need?
What is one force acting on Bubba? Acting which way?
Out.
You got it.
You're here, right? You're on this ride.
Say it again.
Oh, this is the exact
No.
same situation.
No. Towards the wall. What do you mean by towards the wall? Okay? The floor has been dropped out, right? So let's start with this. The floor has been dropped out. Is gravity still acting on you? Yes. So gravity is still acting downward. True? So why don't you slide down? Acting? Oh.
That's crazy.
I'm a freaking beast.
So, how does your frictional force have to relate to your gravitational force? At a minimum, this has to be equal, because if it's not, you're going to start sliding down, which would be bad. Okay? So at a minimum, your frictional force has to equal this. Now there's a third force. Buddy, what's my third force?
Centrifugal force.
Acting?
Inward.
Okay.
At a
Buddy.
diagonal.
Because every day I walk in here, I say, hey, buddy. He says, hey, buddy.
Okay. So that's your centripetal force. Now, in this situation, when Bubba's in a barrel, mu is, you start with this. Mu equals force friction over force normal. What does your force friction have to balance out?
Force gravity.
Gravitation. So I'm going to put that as mg. Your normal force is big. Now your normal force is the force that's acting at right angles to the wall. What's your normal force? Your centripetal force. So that's going to be, masses cancel out. Boom, there you go. Okay?
Is that on the practice review?
It's
Wait,
a centrifugal
what?
force.
Thingy.
Okay, hold on.
That's so wild.
Fn equals F. That makes
So
sense.
wild.
So the force of friction.
Your frictional force
Correct.
is keeping you from sliding
So
down.
that's mg?
I
What
agree
is
with
that?
that.
What did you write?
This,
Yes.
if this frictional force has to balance out gravity's
Yeah.
pull. Gravity's pull is found by taking the mass and multiplying it by
I
your
was just asking.
gravitational
I
acceleration.
can't read your freaking hieroglyphs, dude.
mg.
Thank
So
you.
why can't you write like that all the time? Nobody would have any
So
questions.
wow,
if that
how
was-
does Fn and MAC, how do you know that Fn equals MAC?
So the force normal.
Force normal is
That's a good question.
I mean, force centrifugal.
Okay,
FC
Just like.
Wait, the force normal is force centrifugal.
Yes.
In that case,
Why?
Yeah, that's exactly what I'm asking.
I'm just confused.
Apparently everyone knows the answer.
okay, your normal force always acts at right angles to the surface.
Okay.
we
You're
try
in a barrel spinning around like this. What's the only force that's acting at right angles to the surface?
Yeah, thank you, that was a good.
Which
That
is
was the good
mass
explanation.
times-
Thank you, that's what I wanted.
Literally. Okay, Eric.
That's all I wanted.
two separate, yeah.
Okay,
Yeah, that.
okay. We have two coins sitting on a turntable. Okay?
One's going faster than the other.
Which one is going to take longer to go around?
The one on the furthest end.
Neither's gonna
They're both
take
taking the same
faster.
time.
They're both
Neither
going to
gonna
take
take
the same
longer.
amount of time.
That's gonna be a multiple choice.
Yeah, that's definitely one of the multiple.
That's a multiple choice question. It already is.
He's gonna retype it because of that.
That's an easy question.
So now I got to raise my game. Okay. So, does everybody see why these two coins have the same time of one revolution?
Yes.
Yes. Now, knowing a radius and a value for t, how can you find centripetal acceleration?
I don't know.
4 pi squared r over
T squared.
Okay.
Thank you.
Do they
Thank
both have
you.
the same value of t?
Nah, yeah.
Yes. Yes.
Eric.
After they're
You
squared.
don't get to top.
After
You- no, you don't get to top. So which one has the greater centripetal acceleration? One on the outside, one on the inside? One on the outside, because it has a greater radius,
Wait,
right?
you pointed to the one on the inside.
Huh?
Didn't you just point to the one on the inside of the?
No, I just
Go in.
Oh, okay,
I
you aren't
did-
pointing to one in
Yeah.
specific.
So the one with the bigger radius is going to have a greater centripetal acceleration. So which one is going to fly off?
Can we do that like girl guy separation learning experiment thing?
We're gonna come Monday. There's gonna be a seating
You know what?
arrangement.
That's only gonna
It's
benefit
gonna
the
be like
guys because
Eric,
No.
Kyle,
women
Grant,
don't go.
Reese.
Scores don't go up when they're separated into single groups for the most part, but guys do. Once guys are separated from girls, our scores skyrocket.
Shoulders are
Because we're
distracting.
distracted by
Anyways,
girls are distracted.
so.
Yes,
Yeah, 'cause
the
you
girls
guys
are
aren't.
distracted.
It's so much pressure. Like they're the ones that get to choose the mate, not us. So we have
You
to
know-
be perfect.
Okay,
It's true.
let's just keep Darwin out of this.
You want to know another?
No.
You can't just say let's keep Darwin out of
Yes, I
this. It's
can.
live.
Let's hear it.
This actually.
There's a lot of things that are life that aren't relative to
So
this
when
discussion.
girls are separated, they actually ask more questions too because they're not scared. I know I can be intimidating, but you guys.
Oh, nice.
I know.
Okay. Anyway, back to our story. Back to our story. So, on this one, listen to me, listen to me, listen to me. Mu still equals force friction over force normal. Now, when you look at any of these coins, there's three forces acting on each coin. Meet. What's one of them? Gravity's pulling down. Joseph, what's another one?
Centrifugal force.
Huh?
Centrifugal.
Acting which way?
Inward.
Inward. Now, what's creating that centripetal force?
Friction.
Friction is, right? Because otherwise, if there's no friction, we don't even make it around. So what's the third one? Force normal. Now, in this situation,
This is so much easier than the way you explained it to me. You are saying some crazy stuff, some profound, just theories and.
no, not really. Okay, so your frictional force has to equal your centripetal force because that's what's creating. So on this one, this is my centripetal force. On this one, my normal force is going to equal my
Gravity.
Fg. So with this one, this is mass times my centripetal acceleration. This is m over g. Masses cancel out. So if you're on a flat surface, it's AC over g. If Bubba's in a barrel, it's g over AC. So they're like inverses of each other. So you've got to keep those two thought processes straight. So this is on a flat track. If Bubba's in a barrel, it's g over AC.
AC over G. In a barrel?
In a barrel, this gets flipped.
And
Wait a
on a flat,
second.
then it's
So
that
if it
way.
doesn't have a floor,
Hold your horses.
it's G over AC. But if it has a floor, it's AC.
No. This is like this is like a car that's turning or a flat surface that's spinning. If Bubba has a floor, then you don't need friction because the floor is providing the normal force to hold him up.
Oh, okay.
Okay, then you don't have to worry about friction because the floor is there. Okay, all right. So keep those two straight, and yes, both type problems are on the review. Okay, keep them straight.
Alright, F G over AC if he's
Now,
on a string.
when you look at Kepler's laws, actually, let me hand out some stuff, and then we'll go over Kepler's laws. So stop that.
F G
Does that smell good?
Holy cow, yeah.
We're good.
Okay.
Do you smell that?
Where's the
Smells like,
answer?
smells like.
Where's the answer
It
key?
just smells like pretty gross.
Should I keep it or is it distracting?
So, on this topics from the planetary pundits, let's go over a couple of things.
I'll make the money and she'll just cuddle.
Oh, thanks, babe.
Okay. So, Jupiter has 4 Galilean moons: Io, Europa, Ganymede, and Callisto. So, when you look at this data, you got a period in days, radius in meters. So, if you were to draw a graph and put radius here and orbital periods here, roughly, what's the graph going to look like? Ellie, what was this?
Well, your radius can't be 0, so there's like maximum.
Yeah, so there's a point where we have to start.
Yeah, but then the relationship between the period and the radius is like quadratic, so it's decreasing in like a quadratic curve.
So as the radius is going to get bigger,
They're indirectly proportional to one another.
so you're saying, so as the radius gets bigger, the period
No.
The
becomes
times small.
That's not
Small.
true.
Yes.
No, I lied.
Right?
Look at the period.
Look
No,
at
that's
the data.
velocity. It's
Look at the
velocity there
data.
too.
Look at the data.
Oh.
As the period gets bigger.
Oh, okay.
Yeah, it's bigger.
They're
So-
Big
directly.
period, big period.
As the period gets bigger,
I was thinking
the radius becomes
velocity,
longer.
not time, in my defense.
Okay? Okay. Which happens with our planets around our sun, true. Mercury has the smallest orbital period. Pluto has the longest. Okay? Farther out you are, the longer it takes to go around. Cool with that. So,
Are you supposed to review?
What did they say?
Wait, so is this gonna be like
Read the title.
This one. It's just popping. Okay, that's what I was asking.
it's quadratic?
okay. Now, On that second arrow down below on this page, I've got, using this data, verify that the Galilean moons obey Kepler's third law. So what's Kepler's third law? Ratio of period to radius. So there's any number of ways that you could do this. Pick a couple of the moons. Mr. Taylor, pick 2 of the moons.
Io and Europa.
Okay, so we're going to have the period of Io squared over the period of Europa squared is going to equal the radius of Io cubed and the radius of Europa cubed.
Let's do the period as in 1 IO
Okay.
period.
Now, from this, there's a couple of things that you could do. You could actually plug in these values, square them, divide them, and get a number. Then you could plug in these radius, cube them, get a number. If they obey Kepler's third law, these 2 numbers are going to be the same. You could cross multiply. You could take the period of Io squared, multiply it by the radius of Europa cubed, then see if that equals the period of Europa squared times the radius of Io cubed. You could do that if you wanted to. Okay? You could act like you don't know this number and solve for this. Take this times this, divide it by that, see if it, and then the cube root of it to see if you get this number. There are hundreds of different ways you can solve this. Okay? I wouldn't care. It's just like, hey, pick some data, show that you understand Kepler's third law. Okay? Boom. There you go. Now, the beauty of Kepler's third law is that you can leave these values in days. You don't have to convert them into seconds because this isn't Newtonian mechanics. There's no big G. There's no Newtons.
Straight ratio.
Okay? Yeah, it's just a straight ratio. Kepler didn't know anything about Newton. Newton hadn't done his work when Kepler published his. So there was no discussion about this. Hey, here's the ratios. So you could leave them in whatever units that you wanted. Now, here's what I promise you is going to happen is this third arrow down. What I'm going to say, determine the mass of Jupiter from this data. Pick one of the moons. Okay, I promise you, you're going to have to do something like this on the test. I promise you, I promise you, I promise you. So, what equation relates period, radius, and mass? And it's not Kepler's third law.
GM T squared equals 4 pi squared.
GM T squared equals
4 pi.
squared R cubed. Right? So, this, yeah, it's a Swiss Army knife. So, here's the deal.
Eric.
You have the value of t, but what do you have to convert the t into?
Seconds.
Seconds. Otherwise, you're going
Miles
to get
per
a
hour.
number that is horribly, horribly, horribly wrong. Hallie, pick one of the moons. Callisto. Okay? So I want to find the mass of Jupiter from Callisto. So I'm going to have 4 pi squared R cubed over big G T squared. So I got 4 pi squared. What's the orbital radius of Callisto? No. What are you? 1.8812 times 10 to the 9. Okay. Meters, and then that's going to get cubed. And then I got big G. And then I got. Now, what am I going to have to do with the days? Convert them into what? Seconds per hour. So 1 day, 24 hours, 1 hour, 3,600 seconds. And then here's what you're going to forget to do. You're going to forget to square it. Okay?
You do?
You're going to go through all of this, and then you're going to forget to square it. And then, or you're going to forget to cube this radius. Okay? Those are the mistakes you will make most often. And if you don't, you're either going to get a mass like so large it would be literally a black hole, or you're going to get a mass smaller than our own moon. That's
What's
how
the
far
master
off
one?
this thing is gonna be if you don't forget to square and cube stuff.
I forgot, you said that, yesterday we were doing, we were talking about, what's that point called where like you start accelerating toward the
Lagrange
mean?
one.
Yeah, you said that to calculate that, you would have to know the mass, wouldn't you?
Yeah.
But you said we only knew the mass once we got there, using the pendulum. So how do we
No,
find it?
we had a pretty good estimate of what it was.
How far were we?
I don't know what they actually had. But they had a pretty good idea of what that had to be. They just refined it once they knew the, I mean, there were any number. One of the biggest concerns when we landed on the moon was they were afraid that it was so pulverized that the ship would sink from all the asteroids that were impacting. They literally thought it was, one was a big concern that they thought that it would sink so far that they couldn't leave. That's why they have big, huge landing pads. And when they land, if you listen to what they say, it'll say, hey, it only sank in about an inch. But that was referencing the idea that they were afraid it was going to sink. Okay, so did anybody do this? Okay, well, that's how you're going to do it.
What's the ballpark number? Because I'm really...
I don't know.
Yeah, it's not a computer.
It's gonna be.
Oh, I thought that was...
That's to the 27th.
Like we know.
If I were to
22nd.
ballpark it, I'd probably say around 25, 10 to 25th.
I got 27th.
Yeah,
Does that
okay.
work?
Yeah. Seems
What?
reasonable.
I wish you could.
That was a bad coincidence. So how about that,
How about no?
How about them
the
cubs?
test tube and the centrifuge? That's a good one.
Yeah?
Yeah, let's review
Let's
it.
go over the questions we had yesterday, because I didn't know.
We already did that.
Lunch.
We already did. Okay, so now let me hand out the rest of the review stuff. So, okay, so here's what you have, and then I'm going to turn you loose.
Slow.
Have you guys heard about Isaac?
Happy by the loose.
Okay. So, this is why you have two distinct sets of papers. You have the planetary review, you have the review that has the centripetal motion stuff on it. Two distinctly unique parts. So, when you get to this one on number 3 on the review of the centripetal motion, you have a roller coaster sliding coming down, it's going to hit a loop. Okay, we'll go through some of the velocity stays constant. In reality, it's going to slow down as it goes to the top, but we won't worry about that. So, the first part of this is just finding the velocity at the bottom. I threw that in just for some old school acceleration stuff, get you thinking about that again. Okay, so it's A equals G sine theta. It was simple. You assume that it's frictionless. That's where that comes from. It's an inclined plane. So then, like on this one, you want to feel 1/6 of your normal force weight. So I've got all of that worked out. If you want to do something different when you get this done, go, hey, what would it be if it's 1/2 my force weight? Okay, what velocity do you need? That type of thing. When you get to question number 6, this is one with Bubba's in a barrel, okay? And you're trying to figure out, you know, the centripetal force, minimum amount of friction that you have, all of that good stuff, that's there. On the planetary motion stuff, make sure that you can do, if nothing else, problem number 16, okay, because that's kind of one of the more complex ones. So if you're running low on time, make sure that you can do problem number 16, okay, because that ties in a whole bunch of different things.
What about on the centripetal motion?
Definitely number 3, definitely number 5, definitely number 6.
Alright, 3, 5, 6.
If push comes to shove, and you have a limited amount of time. Okay? Now, if you have I realize I'm being cautiously optimistic, but if you have that big planetary motion assignment done and you hand it in, I'll get it graded, you can pick it up before school Monday. but if nothing else, it is due on
This is
Monday, okay? Due on Monday. If I don't get it Monday, I'm not grading it, okay? So, due on Monday. All right, I'm done, you're on your own.
Alright, can you help me? Sorry. I just have a slight question.
Oh, that's not.
I gotta start